Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's the only way you can keep me going, refreshed and inspired. And of course, don't forget to subscribe. By three-moment equations, analyze the continuous beam shown below by constructing the shear and moment diagrams. Also sketch the elastic curve. EI is 40,000 kN meter square. Note the support movements settlements. So we first transform A into anterior pin and extend it with an interior pin also, so that we apply three moment equations in A prime AB, where moment at A prime is 0. And of course, in preparation for the value of 6 area 2 B over I to L2, you have to consider this strip. This is W minus 30 as to, let's say this is X, equals 15. 45 minus 30 is 15 as to 3. So therefore this is 5x plus 30. And dp is 5x plus 30 dx. And in this strip here, let's call x from the right. So w minus 20 as to x equals 45 minus 20 is 25 as to 3. Therefore, the intensity of this loading is 25 over 3x plus 20. 25 over 3x, or 25x over 3 plus 20. So the differential force is 25x over 3 plus 20. So moment at A prime 0 plus 2 times mb, quantity 0 plus 9 over 1. The moment of inertia is 1. Plus m sub b times 9 over 1. Plus 6 area 1a over I1 L1 is 0 for A prime A span. For AB, we have two values, PB over L, quantity L square minus B square, then divided by I, of course. So integral of quantity 5x plus 30 dx from 0 to 3 times b, which is 6 minus x. If that is x, this is 6 minus x, all over L 9 times 1, quantity L square minus B square. Then for this case, integral from 0 to 3 also of 25x over 3 plus 20 dx. B is x all over L 9 times 1, quantity 9 square minus x square. Then equals 6 times 40,000, because the horizontal line through the middle point A prime crosses A crosses A prime. So HA prime is 0, while HB is negative 30 mm, or negative 0.03 divided by 9. So 6 times 40,000 times quantity 0 plus negative 0.03 over 9. Simplifying this integral, that's 3267. This integral is 3095, and this right side is negative 800. So simplifying, 18 MA plus 9 MB equals negative 5462. Call that equation 1. We then apply three moment equations in A, B, C. So moment at A times, in preparation for the value of 6 area 2B over L2. Let's have that strip, let's call that X. So therefore, W as to X equals 40 as to 6. So therefore, the intensity of this loading is 40 over 6, or 20 over 3x. So the differential force is 20 over 3x dx. So moment A times 9 over 1 plus 2 times MB, quantity 9 over 1, plus 8 over 1.5. The moment of inertia is 1.5. Plus M sub C times 8 over 9.5. Then the value of 6 area 1A over I1L1, there are two integrals. We have integral of 5x plus 30 dx from 0 to 3 times 3 plus x over L9 times 1, quantity 9 square minus 3 plus x square. And the second one, because this is x, so therefore this is 9 minus x. A is 9 minus x. So plus integral 0 to 3 of quantity 25x over 3 plus 20 times 9 minus x over 9 times 1, quantity 9 square minus quantity 9 minus x square, 0 to 3. Then that's 6 area 1A over I1L1, while 6 area 2B over I2L2 is integral of 20 over 3x dx times, this is 6 minus x over 8 times 1.5, quantity 8 square minus 6 minus x square. So if that is x, this is b, which is 6 minus x, 6 minus x. Then equals 6 times 40,000, the horizontal line through b, which is here. So a is above, so HA is 0.03 meter over 9, while C is below B by 15 mm, because this is 45 mm. So negative 0.015 over 8. So equals 6,000 times quantity 0.03 over 9 plus negative 0.015 over 8. Simplifying, this integral is equal to 3314.25. This integral is equal to 2013.75. This integral is equal to 1064, while the value at the right side is 350. So simplifying, we have 9 MA plus 86 over 3 MB plus 16 over 3 MC equals negative 6042. Call that equation 2. Finally, we have three moment equations on spans BC and CD. Take note, moment at D is 0. So we have MB times 8 over 1.5 plus 2 times MC, quantity 8 over 1.5 plus 7 over 2. The moment of inertia is 2I plus 0. The value of 6 area 1A over I1L1 is integral of 20 x over 3 from 0 to 6 dx of times quantity 2 plus x over 8 times 1.5, quantity 8 square minus 2 plus x square. That's A, 2 plus x, while the value of 6 area 2b over I2L2 for span CD is 45 times 4 over 7 PB over L, quantity 7 square minus 4 square, then divided by 2. So 45 times 4 over 7 times 2, quantity 7 square minus 4 square, then equals 6 times 40,000. The horizontal line through C, the middle point. So we have HB 15 mm above and HD 45 minus 18, so 27. So D is 27 mm above the horizontal line through C. So therefore equals 6,000 equals 6 times 40,000, quantity 0.015 over 8 plus 0.027 over 7. So the value of this integral is 1336. This is 2970 over 7, and this one is 9630 over 7. So simplifying, 16 over 3 MB plus 53 over 3 M sub C equals negative 2692 over 7. Call that equation 3. So solving equations 1, 2, and 3 simultaneously with your high-tech calculator. So we have MA equals negative 232.625 kilonewton meter. MB equals negative 141.639 kilonewton meter. And M sub C equals positive 20.991 kilonewton meter. So you can see here moment at C is expected positive because the concavity is concave upward. So that's it. And on the next slide, let's have this to compute for the reactions, shears, and prepare the shear and moment diagrams. So here is the continuation. These are the moments. So let's apply them. The figure shown. Then let's have the reactions. So assuming reaction at A is upward, so summation moment about B equals 0. So let's prepare the shear and moment diagrams. So R sub A considering AB times 9 plus 141.639 rather the moment at B, then equals 232.625. The moment of the 30 kilonewton meter load, uniform load, is 30 times 3, then times quantity 1.5 plus 3, so 4.5 moment arm. So plus 30 times 3 times 4.5. The moment of the triangular load, 1/2 or 0.5 of 3 times 45 times 15 rather. Moment arm is 1 plus 3, so 4. So plus 0.5 of 3 times 15 times 4. And the moment of this 20 kilonewton uniform load is 20 times 3 times 1.5. And the moment of the triangular load is 1/2 or 0.5 of 3 times 25 times 2. 2/3 of 3 is 2. So 0.5 times 3 times 25 times 2. So from there we can solve RA. RA equals 83.443 kilonewtons. Next, we have shear just to the left of B, which is upward minus downward. So shear just to the left of B equals 83.443 minus area of this trapezoid 1/2 or 0.5 of quantity 30 plus 45 times 3 minus area of this trapezoid, which is minus 0.5 of 3 quantity 45 plus 20. So shear just to the left is equal to negative 126.557 kilonewtons. Then for shear just to the right of B, we consider BC, summation moment about C equals 0. Take note considering BC. Shear at B just to the right is positive upward, so that's the sign convention, times 8 plus, so no more, so equals 20.991 plus 141.639. Then moment of the load 1/2 or 0.5 of 6 times 40 times 2. 0.5 times 6 times 40 times 2. So shear just to the right of B is equal to 50.329 kilonewtons. Therefore, the reaction at B is 50.329 minus negative 126.557, or simply add the absolute values. R sub B is 176.886 kilonewtons as shown. Next, for shear just to the left of C, which is downward positive considering BC. So it is shear just to the right of B, which is 50.329. So shear just to the left of C is 50.329. Then minus this loading here, minus 0.5 of 6 times 40. So it is equal to negative 69.671 kilonewtons. While shear just to the right, we consider CD, summation moment D equals 0. So upward positive, so shear just to the right of C times 7, then plus 20.991 equals 45 times 4. So shear just to the right of C is equal to 22.716 kilonewtons. Therefore, reaction at C, 22.716 plus 69.671. And it is 92.387 kilonewtons as shown. Finally, the reaction at D, we sum up moment about C equals 0. Reaction at D times 7 equals 20.991, then plus 45 times 3. So RD is equal to 22.284 kilonewtons. So that's the shear. The shear at D, therefore, just to the left is negative 22.284. So let's now have the reaction at D, then have the shear diagram. So first, go up by 83.440, then constant, then minus the area of this trapezoid, minus 0.5 of quantity 30 plus 45 times 3, negative increasing. So 83.440 minus 0.5 of 30 plus 45 times 3. So we have here negative 29.057. Then minus the area of this trapezoid, minus 0.5 of quantity 45 plus 20 times 3, negative decreasing. Then we have negative 126.557, which is the shear just to the left of B. And it checks here. Then plus 176.886, 50.329, which is the shear just to the right of B. We checks here. Then constant. Then minus the area of this loading, minus 1/2 or 0.5 of 6 times 40, negative increasing. So we have negative 69.671, which is the shear just to the left of C. It checks here. Plus 92.387, 22.716, which is the shear just to the right of C. Then constant, and minus 45. So negative 22.284 constant, which is the shear just to the left of D. Not computed, but mentioned. So plus 22.284, so that closes. Then for the moment diagram, we have negative 232.625 beginning here, going down. So we'll call this x1, then x1 also for the entire 6 meter from here. Call that area 1, this small area here, which is negative, as area 2. This is area 3. Then x2, area 4, then area 5. Those are the areas that we should compute, evaluate. So let's express the intensity of the loading here in terms of x1. So intensity minus 30 as to x1 equals 15 as to 3. So therefore this is 5, 15 over 3 is 5. So 5 x1 plus 30. So that's 5x1 plus 30. Then that's also x1 from this section. And therefore this is, if this is x sub 1, This is 6 minus x sub 1. So therefore, intensity of the load as to quantity 6 minus x1 equals 25 as to 3. So therefore, this is 25 over 3 quantity 6 minus x1 plus 20. So you just apply similar triangles. Remember that our x1 is from this point here up to any section before B. So this is 6 minus x1. So this is W minus 20 as to 6 minus x1 equals 25, where 25 is 45 minus 20 as to 3. That's why we have 25 over 3 quantity 6 minus x1 plus 20. Then for this case, call this x2. So W as to x2 equals, where x2 begins here, 0.0 load, equals 40 over 6. So therefore, this is 20 over 3 x2. That's it. So therefore, shear in AB, beginning here, is equal to 83.443 minus area of trapezoid 1/2 of, or 0.5 of quantity 30 plus 5x1 over 30 times x1. So that's the shear equation, 83.443 for AB minus 0.5 of quantity 30 plus 5x1 over 30, then close times x sub 1. Simplifying and set to 0 to solve for x1 because shear is 0 here. So shear AB is 83.440 minus 30x1 minus 2.5 x1 square equals 0. So from there, x1 is equal to 2.3293 meters. Therefore, area 1 can now be solved. Integral of shear equation dx1 from 0 to 2.3293. So area 1 is equal to 102.448 kilonewton meter. Area 2 integral, same integral except the limits 2.3293 to 6 to 3 rather. So for area 2, to 3 only. And area 2 is expected negative but small, negative 9.619 kilonewton meter. Then shear in from here up to there, up to B. The second shear equation, shear AB1, let's call that shear AB1, is equal to negative 29.057 minus area of trapezoid, 0.5 of quantity 45 plus 25 over 3 quantity 6 minus x1 plus 20 times quantity x1 minus 3. So this distance is x1 minus 3 because x1 begins here up to here, and because this is already 3, so the distance between the 45 kilonewton meter intensity of load and 25 over 3 quantity 6 minus x1 plus 20 kilonewton meter intensity of load is x1 minus 3. So simplifying this equation, shear AB1 is 143.440 minus 70 x1 plus 25 x1 square over 6. So verify that. Therefore, we evaluate area 3, integral of this quantity from 3 to 6. It begins from 3 then to 6, and it is equal to negative 252.171 kilonewton meter. Then shear in BC is 50.329 minus 1/2 of x2 times 20 over 3 x2, then equate to 0 to solve for x2. So x sub 2 is equal to 3.8857 meters. So area 4 is area of parabola if you want, or area by integration. So let's have area by integration. You just check it by area of parabola 2/3 BH. Integral from 0 to 3.8857 of shear equation 50.329 minus 20 minus 10/3 x2 square. If you simplify this, so it is equal to 130.376 kilonewton meter. Then area 5 will not be shown here because we ran out of space. Use the same integral except the limits 3.8857 lower limit, then upper limit is 6. So 3.8857 to 6. Use the same integral. Then area 5 is equal to negative 68.402 kilonewton meter. So we're now ready to sketch or construct the moment diagram by parts. So first, negative 232.625, then plus 83.443 times 3 going up, and the ordinate there is 17.704. Then we have positive plus 17.704 plus area 1, 102.448, so we have 120.152 positive decreasing. Then plus area 2, which is negative increasing, small area here, and the value is 120.152 plus area 2, which is negative 9.619, so it drops to 110.533 plus area 3, which is negative increasing also, so 110.533 minus 252.171, so we have there negative 141.638, which checks moment at B, which is negative 141.639, so that's practically equal. Then plus we have going up straight 50.329 times 2, so negative 141.68 plus 50.329 times 2, we have negative 40.98. Then positive decreasing area 4, negative 40.98 plus 130.376, so that's 89.396 plus area 5, negative 68.402, negative increasing, that's 20.994, which is almost equal to that of 20.991 moment at C. So that's checks. Then 20.994 plus 22.716 times 3 going up, 89.142. Then finally minus 89.142 minus 22.284 times 4, so it's almost 0 there. So this is the bending moment diagram. Let's project points of inflection where moments are 0. So those are the only diagrams. Then we now sketch the elastic curve. So 0 tangent there, positive in this portion, negative, then concave up for this part because it is positive moment in this range. So that's it for this problem, and this is really the last example on 3 moment equations. We will solve this, verify the moments by slope deflections and by moment distribution method in the future.